Welcome to this walkthrough of LeetCode problem number 1829, maximum XOR for each query. In this problem, we'll explore an interesting challenge involving XOR operations and bit manipulation. By the end of this session, you'll have a clear understanding of how to approach and solve this problem efficiently. Let's get started. In this problem, you're given a binary array called nums, which means the array only contains 0s and 1s, and an integer maximum bit. The value of maximum bit determines the largest number you can represent using that many bits. For instance, if maximum bit is 3, the largest number you can represent is 2*3 1 equals 7. This number is referred to as max_number. Your goal is to calculate the prefix XORs of the array nums. The prefix XOR at each index is the XOR of all elements from the start of the array up to that index. For example, the first prefix XOR is just the first element, the second one is the XOR of the first two elements, and so on. Once you have these prefix XORs, for each one, you need to find the integer x in the range from 0 to max_number that maximizes the XOR result when the prefix XOR is XORed with x. The final output should be an array where each element represents this maximum XOR value for the corresponding prefix XOR. The problem also specifies that the value of maximum bit lies between 1 and 20. This means the value of max_number can go as high as 2*21, which is over a million. For the output, you need to construct an array called result, where each element corresponds to the maximum XOR value for the respective prefix XOR. Let's consider an example to better understand the task. Suppose nums is 0, 1, 1, 3, and maximum bit is 2. Here, maximum bit equals 2 means max_number equals 2 squared, 1 equals 3. First, you calculate the prefix XORs of the array, which gives us 0, 1, 0, 3. The next step is to determine the value of x for each prefix XOR that produces the maximum XOR result within the range 0, max_number. This will form our output array. To compute the output array for this example, let's evaluate each prefix XOR and find the x value that maximizes the XOR result. Starting with prefix XOR, 3 equals 3, the maximum result of 3 XOR x occurs when x equals 0, giving a result of 3. For prefix XOR, 2 equals 0, the maximum result of 0 XOR x occurs when x equals 3, giving a result of 3. For prefix XOR, 1 equals 1, the maximum result of 1 XOR x occurs when x equals 2, giving a result of 2. Finally, for prefix XOR, 0 equals 0, the maximum result of 0 XOR x occurs when x equals 3, giving a result of 3. Once you've calculated these values, the results are reversed to follow the problem's requirements, leading to an output array of 0, 3, 2, 3. Now, let's look at another example where nums equals 1, 0, 1, 0, 1, and maximum bit equals 3. Here, maximum bit equals 3 means max_number equals 2 cubed, 1 equals 7. The prefix XORs for this array are 1, 1, 0, 0, 1. For each prefix XOR, we calculate the x value that yields the maximum XOR result. For prefix XOR, for equals 1, 1 XOR x is maximized when x equals 6, giving a result of 6. For prefix XOR, 3 equals 0, 0 XOR x is maximized when x equals 7, giving a result of 7. For prefix XOR, 2 equals 0, the result is also maximized at x equals 7, giving 7. For prefix XOR, 1 equals 1, the result is maximized at x equals 6, giving 6. Finally, for prefix XOR, 0 equals 1, the result is again maximized at x equals 6, giving 6. Reversing these values gives the final output array 4, 7, 6, 7, 6. The problem also highlights several edge cases, such as arrays of size 1, arrays with alternating 0s and 1s, or arrays with all 0s, which you should consider when implementing your solution. To solve problem number 1829, we initially considered a brute force approach, which is intuitive but inefficient. The idea here is to compute the XOR of all elements in the prefix of the array up to the current query index. Then, we would iterate through all possible numbers from 0 to the maximum possible value, which is determined as 2 raised to the power of maximum bit minus 1. For each possible number, we calculate the XOR with the prefix result and pick the maximum value. However, this method involves a nested iteration, one to compute the prefix XOR and another to test all possible values, leading to a quadratic time complexity of O(n squared). While simple to understand, this approach becomes computationally expensive for larger arrays, especially when the size of nums can reach up to 100,000. This inefficiency makes it unsuitable for practical use in scenarios with large input sizes. Now, to address the inefficiencies of the brute force method, we turn to an optimized approach that leverages prefix XOR and bitwise manipulation. The first key insight is that the XOR of an array prefix can be computed incrementally, which eliminates the need to recalculate it from scratch for each query. For example, we can maintain the prefix XOR such that the XOR of elements from index 0 to I is updated as the XOR of the previous prefix and the current number. The second observation is that the maximum XOR for any number can be achieved by flipping the bits of that number, as allowed by the maximum bit constraint. This is mathematically equivalent to taking the XOR of the number with the maximum possible value, max_number. Lastly, instead of processing the queries in the given order, we reverse the order, which is equivalent to removing the last element from the prefix at each step. This allows us to efficiently update the prefix XOR and compute the result for each query in constant time. Overall, this optimized algorithm computes the prefix XOR in linear time and processes each query in constant time, yielding an overall time complexity of O(n). The optimized approach was chosen for its efficiency, scalability, and simplicity. With a linear time complexity of O(n), it handles large input sizes effectively, unlike the brute force approach. Additionally, its space requirements are minimal, making it well-suited for scenarios with memory constraints. The algorithm also scales well with both the size of the input array and the value of maximum bit. Furthermore, the logic behind the approach is straightforward once the key observations about XOR and bitwise operations are understood. This makes the implementation both easy to debug and maintain. A potential trade-off is that understanding the properties of XOR and bitwise manipulation might be less intuitive for beginners. However, given the significant performance improvements, this trade-off is worthwhile. The final implementation begins by calculating the maximum possible value max_number as 2 maximum bit 1. Then, the prefix XOR for the entire array is computed iteratively. Finally, the queries are processed in reverse order to calculate the maximum XOR for each query efficiently. After processing each query, the prefix XOR is updated by removing the last element of the array prefix. This ensures that the prefix remains correct for the next query in reverse order. The result for each query is appended to the output list, and once all queries are processed, the result list is returned. By leveraging the properties of XOR and bitwise manipulation, this algorithm achieves an elegant and efficient solution to the problem. It avoids the nested iterations of the brute force approach and instead relies on a single pass through the array and a simple constant time computation for each query. This balance of clarity, efficiency, and scalability makes it the ideal choice for solving this problem, particularly for large input sizes where performance is critical. To tackle this problem, we're given an array of non-negative integers called nums and a list of queries. Each query specifies a prefix length and an integer x. Our goal is to calculate the maximum XOR value between the prefix of nums up to the specified length and the integer x. Computing this efficiently involves two main concepts, prefix XORs and the tree data structure. First, we pre-compute the prefix XORs of the nums array. The prefix XOR at index I is the result of XORing all elements from the start of the array up to index I. This pre-computation allows us to efficiently determine the XOR of any subarray. For example, if nums is 3, 10, 5, the prefix XORs would be 3, 9, 12. These values represent the cumulative XORs of the array, which will be crucial for efficiently answering the queries. Once we have the prefix XORs, the next step is to insert these values into a tree. A tree is a tree-like data structure where each node represents a bit, either 0 or 1. By storing binary representations of the prefix XORs in a tree, we can efficiently query for the maximum XOR with any given number. For instance, if we insert the prefix XORs 3, 9, 12 into the tree, their binary representations would be 00011, 01001, and 01100. Each of these gets stored bit by bit in the tree. Now, for each query, x, where m specifies the prefix length, we compute the XOR of the prefix XOR at index m with x. The tree is then traversed to maximize this XOR by choosing opposite bits whenever possible. For example, if the query is m equals 2, x equals 8, the prefix XOR at m equals 2 is 12. XORing 12 with 8 gives 4, and the tree helps us adjust the bits to maximize this XOR value. By processing the queries in an optimized order, we can avoid redundant tree constructions. Sorting the queries by their prefix length ensures that we only insert new prefix XORs into the tree as needed, making the process more efficient. The key insights here are, first, that prefix XORs allow us to reduce the problem of finding the XOR of a subarray to a single XOR operation. Second, a tree is a powerful data structure for maximizing XOR values bit by bit, as opposite bits yield higher XOR results. Finally, sorting the queries minimizes redundant computations. In terms of data structures, we use a prefix XOR array to store cumulative XORs and a tree for efficient bitwise traversal. The space complexity for the prefix XOR array is O, n, and for the tree, it's O, n asterisk 32, considering 32 bits per number and n numbers in total. The prefix XOR computation itself has a time complexity of O, n. Building and querying the tree takes O, n asterisk 32, for inserting the prefix XORs in O, q asterisk 32, for processing the queries, where q is the number of queries. This makes the overall complexity O, n plus q, asterisk 32, which simplifies to O, n plus q. This ensures that the solution is efficient even for large inputs. Now, let's consider a few edge cases. For example, if nums contains only a single element, the algorithm must handle this without errors. Similarly, if the integer x in a query is very large, the tree must correctly process up to 32-bit numbers. Finally, if nums or the query list is empty, the algorithm should return an empty result without performing unnecessary computations. These considerations ensure that the solution is robust and handles all scenarios effectively. To better understand the process, let's walk through an example. Suppose nums is 3, 10, 5, and the queries are 2, 8, 1, 6. First, we compute the prefix XORs, which are 3, 9, 12. Next, we insert these values into the tree. For the first query, m equals 2, x equals 8, the prefix XOR up to m equals 2 is 12. XORing 12 with 8 gives 4, and the tree helps us maximize this to 15. For the second query, m equals 1, x equals 6, the prefix XOR up to m equals 1 is 9. XORing 9 with 6 gives 15, and the tree finds the maximum XOR as 11. The final result for the queries is 15, 11. This example highlights how prefix XORs, the tree, and efficient query processing work together to solve the problem effectively. This implementation solves LeetCode problem number 1829, maximum XOR for each query efficiently. The problem requires calculating the maximum XOR value for each query, where the XOR is between a prefix of the array and a number with all bits set, based on the maximum number of bits, maximum bit. Explanation. 1. Maximum XOR calculation. Max_XOR equals 1 maximum bit. 1 computes the maximum possible number with maximum bits, e.g., if maximum bit equals 3, it gives 7, 111 in binary. 2. Prefix XOR precomputation. The prefix _XOR variable keeps track of the XOR of all elements from the start of the array up to the current index. This allows efficient computation of XOR for any prefix. 3. Reverse query processing. The problem specifies that the queries should be answered in reverse order. Instead of explicitly reversing the queries, we process the array from the last element backward. For each query, the XOR of the prefix with max_XOR is calculated and appended to the result list. After calculating the XOR for a query, the last element of the current prefix is removed by XORing prefix _XOR with nums, n1i. This effectively reduces the prefix size by 1 in preparation for the next query. 4. Return result. The result list, which stores answers to the queries in reverse order, is returned as the final output. ### complexity. Time complexity, O(n), since we iterate through the array once to compute the prefix XOR and then another time to process the queries. Space complexity, O(1), as we use a few variables and the result list for storage. This approach is efficient and ensures that the solution meets the constraints of the problem. This is the Java implementation of LeetCode problem number 1829, maximum XOR for each query. The logic mirrors the Python implementation, with adjustments for Java syntax, such as explicit type declarations and array handling. The code calculates the prefix XOR of the array, determines the maximum XOR based on the given number of bits, and processes queries in reverse order. The result is an array containing the maximum XOR values for each query. To solve this problem, we start by understanding the setup for the given example. The array of numbers, nums, is 0, 1, 1, 3, and the maximum bit is 2. This means the largest number we can represent using 2 bits is 3, which in binary is 11. Therefore, our max_XOR value is 3. We initialize two variables, prefix_XOR is 0 to keep track of the cumulative XOR of the numbers, and result as an empty array to store the final output. Next, we compute the prefix XOR by iterating through the nums array. For each number, we update prefix_XOR by performing a XOR operation with the current number. After processing 0, prefix_XOR remains 0. Then, processing 1 updates it to 1. Processing another 1 brings it back to 0, and finally, processing 3 updates it to 3. This cumulative XOR computation sets the stage for the next part of the solution. Now, we process the queries in reverse order, starting from the last index and moving to the first. For each step, we calculate the current_XOR as the XOR of prefix_XOR and max_XOR. After that, we remove the contribution of the element at the current index from prefix_XOR by performing another XOR operation. Let's go through the steps. At I equals 0, current_XOR is 3 XOR 3, which is 0. We append 0 to the result and update prefix_XOR by removing the contribution of nums, 3, which gives us 0. At I equals 1, current_XOR is 0 XOR 3, resulting in 3. We append 3 to the result and update prefix_XOR to 1. At I equals 2, current_XOR is 1 XOR 3, which is 2. We append 2 to the result and update prefix_XOR to 0. Finally, at I equals 3, current_XOR is 0 XOR 3, which is 3. We append 3 to the result and reset prefix_XOR to 0. After reversing the result array, the final output is 3, 2, 3, 0. For the second example, nums is 2, 3, 4, 7, and maximum bit is 3, which means the largest number that can be formed with 3 bits is 7, or 111 in binary. Thus, max_XOR is 7. We begin with prefix_XOR initialized to 0 and result as an empty array. To calculate the prefix XOR, we iterate over nums. After processing 2, prefix_XOR becomes 2. Processing 3 changes prefix_XOR to 1. Adding 4 updates it to 5, and finally, processing 7 brings it to 2. This sequence captures the cumulative XOR values necessary for the next steps. The queries are then handled in reverse. For I equal to 0, current_XOR is calculated as 2 XOR 7, giving 5. We append 5 to the result and adjust prefix_XOR by removing the contribution of nums, 3, which gives 5. At I equal to 1, current_XOR is 5 XOR 7, resulting in 2. We append 2 and update prefix_XOR to 1. At I equal to 2, current_XOR is 1 XOR 7, which is 6. We append 6 and update prefix_XOR to 2. Finally, at I equal to 3, current_XOR is 2 XOR 7, giving 5. We append 5 and reset prefix_XOR to 0. Reversing the result array gives the final output of 5, 6, 2, 5. In the third example, nums is 5, 2, 9, and maximum bit is 4. This means the largest number representable with 4 bits is 15, or 1111 in binary. Consequently, max underscore XOR is 15. We initialize prefix underscore XOR as 0 and result as an empty array. Next, we compute the prefix XOR for the nums array. After processing 5, prefix underscore XOR becomes 5. Adding 2 updates it to 7, and processing 9 finally brings it to 14. These cumulative XOR values are essential for determining the results of the queries. The queries are processed in reverse order. For I equal to 0, current underscore XOR is 14 XOR 15, resulting in 1. We append 1 to the result and adjust prefix underscore XOR by removing the contribution of nums, 2, which gives 7. At I equal to 1, current underscore XOR is 7 XOR 15, which is 8. We append 8 and update prefix underscore XOR to 5. Finally, at I equal to 2, current underscore XOR is 5 XOR 15, yielding 10. We append 10 and reset prefix underscore XOR to 0. Reversing the result array provides the final output of 10, 8, 1. Let's analyze the time complexity of the solution step by step. The first part involves computing the prefix XOR for the array nums. This is done in a single loop, where each element is processed once. Since performing an XOR operation takes constant time, O(1), and there are n elements in the array, the total time complexity for this step is O(n). Next, we process the queries in reverse order. For each query, we calculate the XOR with max underscore XOR, which is 101 operation, and then update prefix underscore XOR by excluding the last element, which is another 01 operation. With n queries to process, this step also has a time complexity of O(n). When we combine both parts, the overall time complexity becomes O(n) plus O(n), which simplifies to O(n). Now let's evaluate the space complexity of the solution. The input array nums is given, so it doesn't add to the algorithm's space requirements. The output array result, however, stores the results of all n queries, contributing O(n) to the space complexity. As for auxiliary variables, we use prefix underscore XOR and max underscore XOR, which are both single integers. These only require O(1) space each. Therefore, the overall space complexity is dominated by the output array, resulting in a space complexity of O(n). When comparing this approach to the naive method, the benefits of the optimized solution become clear. In the naive approach, for each query, we compute the XOR of all remaining elements in the array and then determine the maximum XOR under the maximum bit constraint. This requires recalculating the XOR for potentially large subarrays on every query, leading to a time complexity of O(n squared). The space complexity of the naive approach remains O(n) due to the output array. On the other hand, the optimized solution avoids redundant calculations by using the prefix XOR, dynamically updating it as we process queries. This reduces the time complexity to O(n), while the space complexity stays at O(n). To mathematically validate the big O analysis, let's break it down. For the prefix XOR calculation, we iterate through the array of size n, performing 101 XOR operation per element. This results in a total time complexity of O(n). For query processing, we handle n queries, each requiring a constant number of O(1) operations, one for calculating XOR with max underscore XOR and one for updating prefix underscore XOR. This gives another O(n). Adding both steps, the total time complexity is O(n). For space usage, the output array contributes O(n), and auxiliary variables like prefix underscore XOR and max underscore XOR only add O(1) space. Therefore, the overall space complexity remains O(n). In this section, we highlight some common mistakes to avoid when solving the maximum XOR for each query problem. First, one of the most frequent errors is not pre-processing the XOR prefix. Recomputing the XOR for the range 0, I repeatedly for each query leads to an inefficient O(n squared) solution. Instead, by using a prefix XOR array, you can store cumulative XOR values, which allows you to answer each query in O(1) time. Another mistake is misunderstanding XOR properties, like how a XOR A equals 0 and XOR 0 equals A. These properties are fundamental and can simplify calculations significantly. Large constraints are another area where issues arise. For example, if there are up to 10 to the power of 5 queries, a naive O(n squared) or even n*log, max_vel, solution might time out. This makes analyzing constraints and optimizing your approach critical. Additionally, off-by-one errors in prefix XOR are common. It's essential to remember that the prefix XOR at index I represents the XOR of elements from index 0 to I, so careful indexing is required. Lastly, incorrect handling of the maximum XOR mask can happen when the bitwise nature of the problem isn't fully considered, leading to suboptimal results. By addressing these pitfalls, you can build a more robust and efficient solution. Now, let's look at some interview-specific insights related to this problem. A key takeaway is that XOR problems often involve cumulative operations. Using a prefix XOR array not only improves time complexity but also showcases your ability to pre-process data, a skill that interviewers value highly. Another important aspect is pattern recognition. XOR problems frequently appear in various forms, such as subarray XOR questions, maximum XOR challenges, or even XOR-based tree structures. Recognizing when to use pre-processing or bitwise manipulation is a skill that can set you apart. Furthermore, optimization is a key expectation in competitive coding and interviews. When dealing with constraints, interviewers often look for solutions that leverage XOR properties or advanced data structures like tries. It's also important to discuss the trade-offs involved in your approach, demonstrating a thorough understanding of the problem. To further practice, you can explore related problems like LeetCode 421, which focuses on the maximum XOR of two numbers in an array, or LeetCode 1310, which deals with XOR queries of a subarray. Other challenges, like counting triplets with equal XOR in LeetCode 1442 or finding the maximum XOR with an element from an array in LeetCode 1707, can help you deepen your understanding of these concepts. Finally, let's discuss some alternative approaches and the trade-offs involved. One straightforward method is to use a prefix XOR array and compute the result for each query directly. The time complexity here is n plus q, where n is the size of the array and q is the number of queries. While this approach is simpler to implement, it might not scale well for scenarios involving large XOR ranges or tighter constraints. Another option is the tree-based approach. Here, you construct a binary tree to store XOR values, which enables you to efficiently compute the maximum XOR for each query. This method has a complexity of n*log, max_vel, for building the tree and q*log, max_vel, for answering queries. Although it's more complex to implement, it's optimized for cases with larger XOR ranges. A third approach involves a greedy bitwise construction. In this method, you iterate through the bits of the numbers from the highest to the lowest, greedily determining whether flipping a bit maximizes the XOR result. This provides an efficient solution with a complexity of n plus q*log, max_vel, but it requires a strong grasp of bitwise operations. Each of these methods has its strengths and weaknesses, so the best choice depends on the specific constraints and requirements of the problem. Great job! In this session, we successfully solved LeetCode problem number 1829, maximum XOR for each query. We used prefix XOR to optimize our approach and gained insights into bit manipulation strategies. Thanks for joining, and don't forget to practice and apply these concepts to similar challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!